Motional EMF. We will consider motional EMF by looking at two experiments. So the first experiment that I will consider is a conductor that is moving in a perpendicular magnetic field. So this is a uniform magnetic field, which I denote as B in. You can see that this is moving with velocity v to the right inside this uniform magnetic field. Now, if we look at the forces that will be acting on a free electron in this conductor, due to the Lorentz force QV cross with B, so if you have your right hand forefingers pointing in the direction of velocity and curl them towards the magnetic field into the page, we obtain a force that's going to point up. That's the direction where our thumb points, but since this has a negative charge, it's actually pointing down because the Q is negative. Okay, so this is going to be the magnetic force. As a result of this magnetic force, there will be electron accumulation at the bottom, and there will be a positive charge accumulation on top due to the leftover uncompensated ions in the conductor, and this is going to set up an electric field. So the electric field will point from top to bottom, and in the presence of this electric field, another free electron now will feel a force of attraction towards the top. So the electrical force will be pointing up towards the top of the conductor, but the magnetic force will be pointing down towards the bottom of the conductor. So at equilibrium, these two forces will balance each other, and we will see that there will be an equilibrium voltage set up between the two ends of the conductor due to this net positive charge accumulation and net negative charge accumulation. Okay. So in steady state, the electric and magnetic forces on an electron in the conductor will be balanced, and due to the magnetic force on electrons, the ends of the conductor become positively charged, which establishes an electric field in the conductor. The positive charge on top, negative charge at the bottom. Okay, so what is motional EMF? Motional EMF is the EMF induced by moving a conductor through a magnetic field. So that's exactly this scenario we're talking about in this experiment. The magnetic force the electron feels is QV cross B, that's the Lorentz force, which makes the electrons move downwards, setting up an electric field E pointing from top to bottom. At equilibrium, the electrical force Q times the electric field E in magnitude will be balanced by the magnetic force QV cross B, QVB, because V and B are perpendicular to each other. You can see that the charges cancel, and we see that there will be an electric field set up which is equal in magnitude to the product of the magnitude of the magnetic field and the speed. Then there will be a potential difference between the two ends of the conductor, delta V, which is related to the electric field as E times the length of the conductor. It's E times L, so this will be equal to BV, that's the electric field, multiplied with the length of the conductor. So the established potential difference, EMF, will be equal to BVL. And this is basically due to the relationship between potential difference and electric field. It's the delta V is equal to minus the integral from B to A E dot dl. So going from B to A, dl will be positive, so it's going to be dl j hat if this is the y-axis. Electric field is pointing down. The dot product will give us a minus sign, so minus minus will cancel, and we will obtain E times L as the potential difference. Okay, so in other words, electric field always points from positive potential to negative potential, so it points downwards. Is there a current setup at steady state, but no current since it's not connected to a circuit? This conductor is not connected to a circuit. The loop is not completed here. Therefore, there will be a potential difference built up between the two ends of the conductor, but no current because it's not connected to a circuit. So, in summary, we talked about moving an electrical conductor inside a uniform magnetic field. We see that the charges, the free charges in the conductor, those which are electrons, are subject to the Lorentz force and electrical force due to the electric field setup between the two ends of the conductor. These two forces balance each other at equilibrium, and the electric field that will be set up due to this magnetic field will be equal to B times V, corresponding to a potential difference, delta V, which is E times L, that's PVL. And this is the induced EMF or motional EMF that is induced on this moving conductor. This EMF will not cause a current flow at steady state. Why? Because it's not connected to a circuit. It's just going to be a potential difference built up between the two ends.